Hi everyone, welcome back to Coding with Bharat channel. So last week in the Leetcode weekly contest, we actually had a problem which used an algorithm known as Z algorithm. So I wanted to make a dedicated video explaining that algorithm, its optimized version, and where all it can fit in your use case. So these class of algorithms like Z, your KMP, there is Z, there is KMP, there is Rabin-Karp. These all come under string matching algorithms. So, first of all, what is the problem that we are trying to solve with the string matching algorithms? So let's focus a little bit more on that, and then let's talk specifically about Z algorithm. So a famous problem which is being trying to solve in computer science for a long time is how to efficiently look for a particular pattern, let's say ABA, in a string. So let's say there is a huge string, right? So this pattern occurs, if you see here, it occurs here also. Yeah, if there was an A here, then probably it occurs here. So basically trying to find a string efficiently as a substring in a huge string, that is a problem which is being looked upon from a long time. So the basic way in which you can do this is you go to every position of this string, this main string, let's call it S, and let's call this P, which is the pattern, and you keep on matching with the pattern. So A matches with the first character of the pattern, B also matches, A also matches. So this is one place. Now I go to the next position, which is this B, and again start the matching. So B doesn't match A. So I'll pause this matching. Then I again start matching with the third character, which is A. Again A matches, B matches, A matches. So I get one more possible position where my substring exactly matches, right? So this is the main idea of substring matching, which is a famous problem. Like it has very practical applications at a lot of places. Like even in something like Google search, you are looking for a particular string and it looks for everything in that website and tries to match, right? So even from huge systems to smaller systems, these kind of algorithms have become important, right? So if we talk about this naive approach where we are going through every position and looking for the pattern next, that naive approach is actually n into m in terms of complexity. Like for each position of n length string, n is the size of this major string, I am trying to match m characters at worst case. So m is the size of this p, so n into m. What would be that worst case if we think more about it? Let's say if I have a string having all a's, right? And pattern also has all a's. So actually it will match at every position. So in that worst kind of a case, we'll end up getting n into m time complexity. Okay, so we have talked about the less efficient way. Let's try to see how Z algorithm specifically tries to solve this particular problem. So for that, first we would need to know what is Z array which it tries to create. So let's talk about Z algorithm. And even before that, what is the Z array that we are trying to create? And first, let's talk about how to create that naively, then also talk about how to create that efficiently. So Z algorithm says that we'll create something known as a Z array. What is that Z array? So let's say I have a string like this, which I had previously as well, right? So ABA, BA, DABA, right? Something like this. So at every position, apart from 0th, for every other position, I tried to note down how much of prefix of the string matches with the string starting at this current position. So for example, let's say I take the string starting at B and I try to match it with the prefix of the original string. So even the first character B doesn't match A. So answer here is 0. None of the characters match. If I look at the second position and try to match, this A matches with the first A. this B matches with the second, like first B essentially. Then this A also matches with the third character. Then this D doesn't match with the next character. So trying to look at the string starting at ith position one by one, each of the character, and trying to match it with the starting of the string. So at position number 2 here, index number 2, the A matches with index number 0. Then index number 3, which is B, matches with index number 1, which is again a B. Then index number 4, which is another A, matches index number 2, which is another A. When we go one step further, index number 5, which is D, doesn't match with index number 4, which is B. So yeah, that is where the loop breaks and we get three characters now matching at this A. So as you can see also, ABA and ABA. Right? Again, let's look at B, the next position, which is this B. Again, it doesn't match with the first character, so answer is 0. Let's start here. A matches with the first A. The next D doesn't match with the B, so answer is 1. Let's look at the D also. Again, it doesn't match with the first character, so 0. Last A matches with A, B matches with B, A matches with A, so 3 match, but rest is not there in the like second string, right? So answer here is 3, similarly 0, and here 1. So this is the main Z array. So what is Z array? If I talk about Z of I, so Z of I stores, if I look at string from I till the end, and if I look at the string starting from 0 till the end, how many characters from the start of both the strings match? So substring from I till the end and the entire string, how much of prefix matches between these two? That is what is stored in Z of I. So this is the main idea, what we are trying to store in Z of I. Okay, let's think about brute force. How would we go about writing something like this as a simple brute force? So the answer for that is, I'll run a loop I equal to 1 to n, right? I want to calculate Z of I for every I. Now, to calculate the result for ith element, I would need to start something like a 2 pointer starting at 0 and starting at I, matching the characters. So I'll say, let's say count is 0 as of now. So while my so yeah, let me create two more variables. Let me write it a little better. So yeah, so we'll have a count equal to 0. I'll have probably variables j equal to 0 and k equal to I, right? Two variables, one at 0, one at I. Now they'll keep on moving forward and matching the characters. So while k is less than n and s of k, kth character matches the jth character, then you do j plus plus and k plus plus. So simple idea, till these two matches just keep on moving forward until k doesn't reach the end. So now finally in if you look at the variable j, it will have the number of characters that have matched. So probably what I'll do is I'll store z of I equal to j, how many characters have matched. So yeah, this is how you can write it naively, where for every index you keep on comparing from the start, counting the number of elements which are same. So I don't think we also need the count, because at the end of the day j is giving us the count, so that is enough. So yeah, just keep on matching till you are able to match. When you are not able to match, you break from the loop, and now whatever is stored in j is the number of characters that actually matched, right? So yeah, that is about naive approach. Okay, now let's talk about the time complexity of this naive approach. So if I think about it, this is again very similar to what we did in brute force of string matching, and this is in fact n square, right? Like for every position, your entire substring might match, right? In case of all A's, and then it would become n square in nature. So we need to optimize this calculation of Z more and let's talk about that. How do we go about it, right? Okay, so I'll take another example and explain it. So let's say we have a string a b c d a b c and a b c. Okay, so let's say I try doing some calculations here, right? So for an answer for A is initially 0, for B also 0, for C also it doesn't match 0, for D also it doesn't match 0. Now for this A, we see A, B, C entirely matches with this. So answer is 3. Till here, we can brute force also and it is still fine, right? Okay. Now, Now, if you think about it, when we are at A and we have calculated the result for it as 3, we have actually seen the next few characters. We have seen that next character is B because it actually matched with this guy. We know the like next character even to that is C, which actually matched with this guy. So actually, if you think about it, when we have calculated the result for this as 3, we are aware of that. Okay, from 0 1 2 3 4, from 4 5 6, from 4 to 6 the string matches with the initial part, right? The string matches with the initial part. So now to calculate the result for this fifth character, we don't need to start a loop again, but what we can do is we can leverage the values calculated at that prefix. So at this B, we would have already calculated the result as 0, so we can just copy paste it. So what I'm saying is, if I have already seen some ith index result, right? If that ith index is being included in your range which you have already seen. So what is the range that you have already seen? 4 to 6. So 5 is within this range. So since you have seen it, that same character, same string of characters would have occurred in the past, and you can copy the result from there. So you already know this B, this BC, which is there, has occurred in the past. And we have calculated the results for both B and C as 0. So I can just copy paste it and not do it again. Similarly, I'll go about doing it here. So when I go to this A, I again start comparing. Okay, A matches, B also matches, C also matches, right? So I'll put 3 here. Now my L2R becomes that, okay, from 7 to 9, I've calculated my result. So for values in 7 to 9, like 8 and 9, I'll keep I'll keep copying the result from the past. So when I try to calculate the result for 8, we know that 7 to 9 matches 0 to 2. So 8 means 1 and 9 means 2. So that is how we can save some computations by reusing the results in the past. This is not the complete solution, but this is the major idea on which Z algorithm is based upon. That, okay, if you reach a particular index and you see that you have never calculated anything for this, like this has not been calculated as part of the previous characters, then what you do, you recalculate it like you have always done, like with the brute force. So as an example here, when we started at when we reached this A, previous values were 0. So we had not seen this A in the past. This is the first time that we are seeing this A. So I'll go ahead and run the brute force and calculate the result for this A. So I'll match this A, I'll match the next B, I'll match the next C, and store the result as 3. Right? Simple. But now if you arrive at such an index for which you have already done the calculation for some other index in the past that encapsulated this particular index, then probably reuse the values from the past. So that is the major idea on which Z algorithm is based upon. So in a way, what I do is I maintain an LNR which are initially 0. I'll run the same loop, I equal to 1 to n. If I see that my index is more than r, right? If it's a new index that I'm seeing, or even greater than for that matter, Then what I'll do, I'll recalculate zi with brute force. Otherwise, in the else case, what I'll do is I'll try to use the value from the past. So what is that value from the past? Actually, if you think about it, I can simply replace z of I with z of I minus L. Okay, I minus L. Why I minus L? So L2R matches with 0 to whatever is the difference, right? R minus L, 0 to whatever the size is. So if I do I minus L, right? So let me just go and visualize this for you. So let's say there is a string. There is this portion L2R which matches 0 to how many characters would be there? R minus L, right? These many characters would be there. So when I want to look at Z of I, how do I calculate it? I look at the difference between this L and I and go to that much plus from 0. So it's like 0 plus I minus L. So that is what I've written here. 0 plus I minus L, which is Z of I minus L. That is the main idea. Oh, I've written L minus L here. Let me correct it. So this is going to be I minus L. Right? So I minus L to get this difference and add it to 0 to reach the corresponding character here in the prefix. So this is the basic idea. But this idea fails for one or two cases. So I'll talk about this. Like you cannot directly copy. Like if some of you have been spending some time trying to visualize this, you'll see that this would actually fail for a lot of cases. We cannot directly copy the values. What if there are more characters that match, or what if that there are less characters that match? So I'll cover both these scenarios right now, right? Okay. So first let's talk about what if less characters match, right? And I'll talk about the scenario where this can happen, where the answer is actually less than z of I minus L. Okay, so z of I minus L is a good estimate for most of the scenarios, but there could be some scenarios where the answer would be either less than it or more than it. So I'll talk about both the scenarios here. So let's take a string, right? So let's take a simple string. Let's say AAAB. Okay, simple string AAAB, right? Or let me just add a few more characters, just some dumb characters. Okay, yeah. So now here the answer is 0, z of I is 0. I reach the first index. How do I go about it? Start comparing from the start. So A matches with A, next A also matches with A, B doesn't match with this A, right? So if I think about it, this A matches with this A, then this A matches with this A, then this B doesn't match with this A. So answer for the next index is 2, because two characters match. Two A's, as you can see, matches with the first two A's, right? Now, when I try to calculate the result for this third index, if you see L2R, what is L2R? I've calculated the result from the first index to second index, right? Calculated the result from first index to second index, like first two characters, like sorry, second and third characters, right? So when I'm going at index number 2, this is index number 2, I see that it is within L2R. It is within L2R, so I'll try to reuse the value. What value will I reuse? Z of I minus L, so 2 minus 1, so Z of 1. So I'll say whatever the result is for first index, since it matches, you just copy it to 2 here. But if you think about it, this 2 is wrong now. Why? Because AB doesn't match with AA. Okay. So let's think about why it happened. Why it actually happened that because we had a solid plan, right? We had a pretty solid plan that we would copy the back result because they have seen the same characters in the past. So the result for them could just be copied here. But the plan fails because of a very simple reason, that actually when you were calculating for this A, the second A, you had only seen the next two A's in the picture. This A and the next A. These two things only. When you are putting the result for this A, then you are saying that you are also including one character that you have not seen so far. So the answer should never move like go beyond the current R that you have seen, right? So the answer should never go beyond the current R that you have seen. So let me increase the number of A's here to make it a little bit more better, right? So let's say there are 5 A's, okay? And then there are some trash characters, okay? So now for this A, when you think about it, 4 of A's will match with the initial 4 A's. So answer for this would be 4, right? When I'm calculating for this, I'll see that, okay, I have seen this character in the past. It matches with this character from the prefix, right? It is the second character in the string from the string that we have seen, L to R. And the second character is same as the prefix second character. So copy the result there. So copy this 4 here. But the problem is the 4 characters from here are what? These 4, out of which I've never seen this B in the past. Like I only saw when I was calculating for this A, these 4 A's. These 4 A's were what matched the prefix. But the next B, I never matched actually from the prefix. So you cannot put a value here which goes beyond the boundary that you have seen so far. So it should never go beyond R, right? So that is why it's important. If your I plus Z of I, if index plus whatever value you are putting there, if it goes beyond R, then limit it to just R. So put Z of I as just R, right? Just so that it goes up to R. So this is the first case where we might get a wrong answer when I'm just copying, because that past string only saw till a particular length, but that particular length goes beyond the current boundary at R. So this is an important step, that we need to reduce the Z of I value if in case we are going beyond R. Okay, let's take the other scenario where the answer goes forward from R, right? So answer is more than Z of I minus L. So for this, I'll take this string. So let's say I'll take the string as, yeah, AB, AB. Let's take AD, right? And then there is again AB, 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 and AD, right? So a huge string. But let's try to do our calculation, and we'll also get thorough with how Z algorithm works, right? So I start here. It is 0. B is a new character, so my L and R are still 0, right? B is a new character. It is beyond R. So I'll calculate the result. So B doesn't match with A. So answer will be 0 here also. Then I reach this A. Still R is 0. So my character is more than R. So I'll have to do the calculation again. So A matches with A. B matches with B. A matches with A. D doesn't match with this B. So answer for this will become 3, right? Because ABA matches with initial ABA, right? So answer here becomes 3. Okay. Now when I want to calculate for this B, what I'll do? We have already seen this ABA. So my L is 0, 1, 2, and R is what? 4, right? And I am at currently character number 3. So for character number 3, I can reuse the value calculated at character number 1. So I'll go back to 1 and put that value here. So 0, I'll put it here. For character number 4, still I have seen it. So I'll try to copy the value in the past, which is the value 3 here. But I'll see if I do plus 3 from this A, it goes beyond the boundary, right? And which we can see also ADA doesn't match with ABA, right? So it is going beyond the boundary. My boundary is at this R. So I'll replace the value with 1, the lesser case that we have seen in the past. Okay, so 0, 0, 3, 0, 1. Till now we are doing good. D is across the boundary. Like our boundary was at 4, so it is beyond the boundary. So we have to recalculate it for it, right? So for this D, I try to recalculate. I match it with this A. The answer is 0, so I'll put it 0 here. I go to this A again. It's beyond the boundary, so I have to recalculate for it. So I start my calculation. So A matches with this A, B matches, another A matches, another B matches, another A matches. The last B doesn't match. So I put a value of 5 here, right? 5 characters match. A, B, A, B, A, A, B, A, B, A. So 5 characters match. And now my L2R becomes that okay, 0, 1, 2, 3, 4, 5, 6. From 6 to plus 5, 7, 8, 9, 10, 11. So 11. 6 to 11, for all of them, I'll just reuse the previous value calculated. So for 7th character, I'll reuse the value here 0. For this character, I'll reuse the value this as 3, right? As you can see also, ABA matches with ABA, but ABAB doesn't match with, yeah, does it? Does it match? Yes, it matches. So if you see, this 3 that we have put here, this 3 that we have put here is now restricted by the 3 that we had seen in the past, right? But what can very well happen is that now more characters are actually matching, right? So if you think about it, the 5 that we saw here, this 5 had this boundary. But now when we are at this A, actually more characters beyond this boundary start matching. So one more step that you need to do whenever I plus zi reaches the boundary, you can start looking for more characters that are matching and update your boundary. So what I'll do is I'll say that okay, these 3 match, well and good. Let's try to match the 4th one. 4th one matches, 5th one also matches. So I'll replace this answer with 5 and replace my boundary also to represent the new part that I have seen. So this will go to 8 and this will go to 13. So two cases you need to do. First, maintain an LNR, the last boundaries that you have seen. Whenever you are at certain index I, you just copy the value. There are two cases. First, you are beyond the boundary. If you are beyond the boundary, use your brute force to calculate the result. When you are within the last boundary, you copy the value from the past. Now, if copying the value from the past lead you to go beyond the boundary, then restrict it within the boundary, because that is not, that is unknown, that we have not seen as of now, right? Now, after doing all of this, try to expand the boundary and see if more characters match now, right? Okay. So that is the whole idea of Z algorithm, that use the past values and try to increase or decrease the boundary based on certain conditions. Cool. How is it when? For each index, I'm calculating the value once, right? So I'm going through each index once. And if you think about it, once I match till a certain boundary, I'll not be recalculating the results for those. Like I'll only be expanding the boundary further, right? And reusing for all of these the previous values. So actually, if you think about it, it's like a two pointers. Like we have an L and we have an R. We calculate the result and expand our boundary, right? For them, I can recalculate from the past values. So L also moves forward, which is our loop variable, right? And sometime we'll see that okay, we can match more characters, so we'll again start expanding our boundary. So main idea is it's like two pointers which are moving forward till the end. So if you think about it, it's actually going to be O of n. Okay, so this is a difficult algorithm first of all, so spend some more time on it, I would say, right? But it's an important algorithm for string matching. I would say this is much easier than KMP. Like I always felt KMP as the toughest one. So yeah, spend some time on this and you'll be actually able to visualize how things are happening. Let me also go through the code once quickly on how we go about it. Before that, how do we actually solve the problem that we talked about in the past? Pattern matching, right? So main idea was that we want to see in a huge string, let's say BA, 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 how many places we have our pattern which is ABA, right? This is the main problem that we were trying to solve. So for that, what you do is you put your pattern in the beginning of your string with a dollar or with a trunk trash character, right? Which will never be in the string. So what will happen with this? Now when you run Z algorithm on this new string created by pattern dollar the actual string, what will happen? Z of this position would be 3 because 3 characters match. Similarly, Z at this position will also be 3. So wherever your Z of I matches your pattern length, those positions are the one where that many character matches the starting is what the pattern. So that is how this Z algorithm or Z array is used for your pattern matching. Okay, let me illustrate it with the help of code and dry run it on an example also, right? Okay, so this is my Z match function, so let's look at that. This is the main function that we wrote. So what I've done, I've declared a Z array with size as the size of the string and all the characters as 0. I have my L and R initially as 0. So we have not discovered any part of the string apart from the 0th character. Then what I'm doing, I'm running a loop from 1 till the end. So calculating Z of I for each of the positions. So first thing, if the character that I see, if the index that I see is within the last boundary, which is R, then I will reuse the value. So I have done Z of I is equal to Z of I minus L. This is what we wrote, right? So answer for this is can be drawn from the prefix where we have already calculated the result for those, right? So that is what I did. Next, we need to handle the case where Z of I takes you beyond the boundary of what we have seen so far. So if your I plus Z of I current index plus the number of characters, they go beyond R, then that means you need to restrict it to R minus I. Just restricted within R minus I. What is R minus I? Why R minus I? So R minus I is the number of characters between the current index and the boundary, right? That is what R minus I is essentially. Okay. Once you are done with this, so you have stringed the boundary, then you start matching more characters and start looking if more characters can match. So what I've done, if I plus Z of I, the number of characters that we have seen, is within the range of my string, and we see that S of Z of I, like prefix at Z of I, matches with the new character that we see, that is I plus Z of I. If these two matches, then we keep on increment our Z of I, right? So why S of Z of I? Let me talk more about it. What does this mean? So let's say we had the case that we talked about, right? A B A B A D A P A B A B A B A, right? So let's take this. So right. So if you think about it, what happened? We had 3 here, then we had 0, then not 3 actually. I started with 1, 2. Okay, so this is going to be 0, this is going to be 0. Then this ABA matches, right? So 3, then 0, then 1, then 0. Then here when we saw, we had 5. So ABA, BA matches. So 5. Then for this B, we recalculate this 0. For this A, we look back again 3. Now, what is I? The position of this 0, 1, 2, 3, 4, 5, 6, 7. So 7. So 7 plus 3 is 10. So 7 plus 3. So 8, 9, 10. This position. If this position matches with 3, 0, 1, 2, 3, right? Then that means there are more characters that we can match. So that is what I've written. S of Z of I. S of Z of I is this position. Like Z of I is the number of characters that match from the start. So S of Z of I will be the position next to that number of characters that match. So if that is equal to the new character that we can take into our boundary, I'll do Z of I plus plus. That okay. Start taking more characters. And now, if our boundary has updated, if I plus Z of I has gone beyond R, that means for this I've calculated a new high that we have seen so far. So I'll replace my L to I and R to I plus Z of I so that this becomes our new boundary. So update our boundaries. So that is the high level code of how we go about it, right? So yeah, this is O of n. Why this is O of n? Because like whichever values are within the boundary that we have seen so far, within the R that we have seen so far, we'll just calculate it in O of 1. Apart from incrementing the boundary. Incrementing the boundary, then our R will update and new values will be in O of 1, right? So yeah, that is how it is, O of n in nature. Okay, let's look at the result also. So I've called Z match with the pattern, which is ABA with the string. So if you actually look at it, we have a 3 here, which is for this position, right? The 0, 1, 2, 3, fourth position, which is the fourth position in our string. Then we also have another 3, and then also we have another 3. And you can see that those 3 are there. So this is ABA where it matches. Then there is this ABA where it matches. And then there is this ABA where it matches. Okay, and you can compare the results of the remaining characters also and try out running multiple cases on this algorithm, so you'll see that it works. Cool, then I hope you got an idea about the algorithm, Z algorithm in general. So now I hope you'll be able to solve the fourth problem from the last contest, right? So yeah, but do practice some more problems. I'll link 2 more problems on Z algorithm in the comment section or the description. So do go check them out. Do implement Z algorithm, right? Cool, then. See you guys in the next one. So prefix sum is pending from my side for this week. So there will be one video for prefix sum algorithm as well. So probably expect it tomorrow. Okay. Bye bye everyone. See you tomorrow.